This video is going to serve as an introduction to our capacitor lab. You might ask, what is a capacitor? Well, it turns out we've already been talking about these things we call capacitors. It's basically just two pieces of metal, two conductive plates that are either separated by air or separated by an insulated material. And the context that we've talked about them, we know that two parallel plates, when there's a positive and negative charge on one and the other, there's a uniform electric field set up in between there. Well, this thing is a capacitor, and it might not look like two parallel plates, either neutral or charged, but inside of here are two pieces of metal, one connected to this terminal, the other one connected to this terminal, and they're separated by a very small distance by an insulator, so it doesn't allow the charges to go. And we could put a net positive charge on this terminal and a net negative charge on that terminal, and then in between those two plates there would be a uniform electric field set up inside of there. And so we're going to be just exploring more about capacitors, like how do we get them charged and what can they do. So in order to create a net positive charge on one and a net positive charge on the other, we need something that's going to force charges, negative charges, from one conductor to the other. If there's missing electrons on this one, it's going to have a net positive charge, and if those excess end up there, it's going to have a net negative charge. We also know that if one is positively charged and the other one is negatively charged, and there's an electric field in between those two plates, that means there's an electric potential difference between the positive plate and the negative plate. The positively charged plate would have a high electric potential, and the negatively charged plate would have a low electric potential. So if I want to turn these two things that are both neutral right now into a charged positive and a charged negative plate, we need something that's going to force an electric potential difference between these two things. Well, it turns out we've already talked about one of those things. An electric power supply, you can actually adjust if you hook two things, one thing to the black and one thing to the red terminal. This can force a specific amount of electric potential difference between the things touching those two terminals. Well, we also have another thing which can force an electric potential difference, and that's just a battery, a chemical battery. This is a D cell, and the function of a battery is to create an electric potential difference between whatever's touching the negative side of the battery and whatever's touching the positive side of the battery. So just to confirm that, let's use one of the measurement tools that we've already talked about when we were mapping electric potentials around different charge distributions. It's our multimeter, or our electric potential difference meter. That's one thing it can measure. So if I turn this thing on, remember this value right here will be electric potential difference between what the black lead is touching and what the red lead is touching. So I'm going to put the black lead on the negative side of the battery and the red one on the positive side of the battery. And you can see that our meter says there's an electric potential difference of about 1.6 volts. So that means the positive side of the battery has 1.6 volt higher electric potential than the negative side of the battery. So if we had a positive charge and we placed it there, if we had 1 coulomb of charge, 1.6 volts is 1.6 joules per coulomb. That 1 coulomb of charge would have 1.6 joules of energy placed at that location and 0 when placed at that location. Okay, so batteries create an electric potential difference. So let's use this battery to create an electric potential difference across these two neutral conductive plates. So we're going to charge this side net positive and this side net negative. So to do that, I'm just going to use some conductive wires. I'm going to hook one side to one terminal. And the side I want to have at high potential, I'm going to use our red wire. And the side that I want at low electric potential, I'm going to use our black wire. So I'm going to use the red wire to connect one terminal of the capacitor to the positive side of the battery, and the black wire to connect the other terminal to the negative side of the battery. I'm just going to wait for it for a while. And what that battery does to create the electric potential difference is that battery forces electrons off of the red side towards the black side, creating a high potential on the red wire side and the low potential on the black wire side. So that should be long enough for the battery to do its job, to create an electric potential difference. So now let's just confirm that this capacitor is charged. This side has a net positive charge and this side has a net negative charge. And let's do that with our electric potential difference meter, or a potential difference meter. So I'm going to put this on the black lead on that side, the red lead on this side, and you can see that there is a 1.6 volt difference from the negative side to the positive side. Okay, so we've just separated charges. We've moved electrons from the which is now the positive side, to the negative side. So the question is, how can we get this thing back to neutral? Well, if there's an excess amount of negative charge here, they're pushing each other away, and they want to get to a place where there's missing electrons, but they can't do that through the air. We need to provide a conductive pathway from the negative side to the positive side. So I'm going to do that, except I'm going to put something in that conductive pathway. If we just touch these two things together, the excess electrons should go from the negative side back to the positive side, and everything should just end up neutral. But I'm going to put just a little light bulb in between there. And a light bulb, a traditional light bulb with like a little metal filament inside of there, that filament is just a really thin wire. And so if I connect one side of the wire here to this side and the other one to there, it's going to force those charges that are going to go from the negative side to the positive side through that little filament. And a filament, the purpose of a filament is to basically produce light when charges go through it, because when charges move through it, that little tiny filament heats up so much it actually gives off light and heat. So let's go ahead and do that. Our connection is made now. Okay, might have been very difficult to see, but it lit up for a little bit and then it quickly went out. And so that filament only lit up for maybe a second and a half or so. That's all the time it took the electrons to go from one side to the other. And that means this capacitor should now be neutral. Both things should be neutral, which means there should be no more electric potential difference between the two plates. And we can confirm that with our electric potential difference meter. That says 0.1 volts, or 0.1 joules per coulomb. Pretty much we've discharged this thing. Things have gone back to neutral. Okay, well, we could put, not just a 1.6 volt electric potential difference across there. We could create a larger electric potential difference if we can move more electrons from one side to the other. We can keep forcing them on there. We should be able to get more charge stored by this capacitor, which could basically flow through a light bulb. So let's just find out how to do that. If we take one battery, that was forced an electric potential difference of about 1.6 volts. If we take two batteries, we can essentially force there to be an electric potential difference of about 1.5 volts. And then if we connect another one kind of in a row like that, this one's going to increase the electric potential difference by about 1.5 volts. And this one will increase the electric potential difference by about another 1.5 volts. And so using two batteries kind of stacked in a row, we should be able to get a greater electric potential difference across these capacitor terminals. So I've got our two batteries in a row, and I'm going to just connect them to the capacitor. And let's use our meter to find out, is this capacitor charged, as evidenced by an electric potential difference. So black on the negative, red on the positive side. Yeah, we've got a 3.1 volt difference, so it's about double what it was. So using two batteries means we can create double the electric potential difference. And using three batteries, we should be able to create triple the amount of electric potential difference. So now that this has a higher electric potential, that only happens if there were more electrons that were moved from one side to the other than before, which means if we now connect conductively, make a pathway through this light bulb, the electrons can go from the negative side to the positive side, and there should be more of them, and so this should light up for a little bit longer if that's actually the case. So let's try it. 3, 2, 1, go. Okay, that should have been a little bit clearer. It lasted longer and it was brighter. And so that's evidence that this thing did have more charges stored in it, or separated, and when we provided a conductive pathway, there were more charges that flowed from the negative side to the positive side. Okay, so just from those two little demonstrations, there seems to be a relationship between the potential difference that's across two capacitor plates and the amount of charges that are stored in it. Now, we're not like adding charges, but we're taking charges from one side and moving it to the other side. And so if we took, if we moved 1 coulomb worth of electrons from the positive side to the negative side would have a net charge of -1 coulomb, and this side would have a net charge of +1 coulomb. And so even though we're not adding electrons or taking electrons away as a whole, we'd say that this is storing 1 coulomb of charge, because that's the net charge on each of those plates, one being negative and one being positive. And if there's a greater electric potential difference that's applied across these plates, forced by the battery or the batteries, then there was a greater net negative charge and a greater net positive charge. So there definitely seems to be a relationship between the potential difference across capacitor plates and the amount of charge stored by that capacitor. And that's what this lab is going to have you guys investigate. What is the relationship between the electric potential difference across the plates and the amount of charge stored by that capacitor? Some groups are going to be using these bigger capacitors. Other groups will be using these smaller capacitors and answering that same question. How does the electric potential difference change how much charge is stored by this, or how much charge is stored by this smaller capacitor? Before you guys jump into it and start collecting data, we need to talk about, well, what is the data we need and how do we actually get that data? If we take our capacitor, we have to set up an electric potential difference, and we've already talked about how to do that. We're going to use a battery, or 2 batteries in a row like this, or 3 batteries in a row, or 4 batteries in a row. We can keep doing this to apply, to force the plates of the capacitor to be at different electric potential differences. But the question is, how do we know how much charge is actually stored by that? Like, we just used a little light bulb to kind of qualitatively figure out, hey, there's got to be more charges because it lit up longer or it lit up brighter, but we want to get a specific quantity of charge measured in coulombs. For this electric potential difference in volts, or joules per coulomb, we want to know how much charge is stored as measured in coulombs. So I'm going to go ahead and charge this capacitor using, let's use 3 batteries. So let's create a little bit larger electric potential difference across those plates. So I'm going to hook it up to our capacitor. It takes a little bit of time for those batteries to do their jobs to create that electric potential difference. Okay, so give it some time, then stop, and then this is the way that we check, is there an electric potential difference, using our electric potential difference meter. And it says we've got an electric potential difference of about 4.6 volts, which is about triple what 1.5 volts is. So that's what we would expect for 3 D-cell batteries like that. So now that we have this electric potential difference, one data point is, hey, it's got an electric potential difference of 4.6 volts. So the question is, for that electric potential difference, what is the net charge stored by this capacitor? Net negative charge on the negative side and net positive charge on the positive side. Well, we need a way not just to kind of know qualitatively what's going on with the light bulb. We need a measuring device that can measure or help us figure out the amount of charge that ends up flowing from the negative side to the positive side. Okay, and we're going to actually use this measuring device. This is called a current meter. It measures current, and current is defined as the amount of charge in coulombs that flows through this device each and every second. So it's kind of like, it's called like the flow rate, the amount of charge per unit time which goes through the meter, or is flowing through this one path from the negative side to the positive side. And so I'm going to hook this thing up, and then we're going to talk a little bit about how we can actually get that measurement of charge. Okay, so let me just verify that this thing still has an electric potential difference of about 4.6 volts, or about 4.5 volts. And what I'm going to do is I'm going to hook up a conductive pathway. Okay, I actually flipped our capacitor around. The negative side's here, so the electrons are going to flow through here. Okay, once I connect this wire to our meter, it's going to go through our little sensor, measuring the amount of coulombs per second, and it's going to flow through here. And I've got just a little device right here to kind of slow down that flow, to increase the amount of time that this capacitor gets discharged, where everything goes back to neutral. So it will be a little bit easier for us to actually quantitatively measure the amount of charge. And then it's going to go here, and in the end, everything should be neutral. Okay, so I've got Logger Pro up and running so that we can get a real-time readout of the current, the amount of coulombs per second as time goes on. So let me go ahead and get that running. And I'm going to connect this in 3, 2, 1, go. Okay. You can see that the current, the amount of coulombs per second, was very high initially, and then as time goes on, now after about 20 seconds after it's been connected, there's less charges per second that are flowing through there, right? If we look at the electric potential difference on our meter, you can see now that we're down to an electric potential difference of about 0.3. The electric potential difference goes from what we started with, about 4.5 volts, and it'll eventually go down to 0 once all of the charges have had a time, all the electrons, the excess charge, have had enough time to basically neutralize or move over the positive plate, and everything becomes neutral. Okay, and because this little device here is here that slows down that flow of electrons from the negative side to the positive side, it's going to take a little bit of time. And once the current goes to 0, the amount of coulombs per second, then we can disconnect this and just talk about how do we get that measurement from that graph. In order to determine the amount of net charge stored in the capacitor in this case, we need to look a little bit closer at our current versus time graph. Remember, current we defined as the amount of charge flow, or the amount of charge which flows past a point each second, in this case through our current meter. We use a variable I to represent current, and like I said, the units of current are coulombs per second, or 1C divided by S. A coulomb per second is defined as an ampere or amps, and so when you look in Logger Pro, the current is measured in units of A or amps, but remember that just means coulombs per second. This is actually another equation we have on our AP Physics 2 equation sheet. It's current is equal to some change in charge, or some charge that flows past a certain point, divided by the amount of time it takes that charge to flow past that point. So we're directly measuring current using our sensor, and you can see this is how the current changed over about 70 seconds. But we really want to get from this graph not the current at any given time. We want to know the total amount of charge which flowed through that sensor, in the about 70 or 80 seconds. And so if we rearrange this equation for Q, let's see what happens, right? If we multiply each side by delta T, we get that the amount of net charge that flowed past a given point would be equal to the current multiplied by the time. Right? If the current was constant, we could multiply some value, times 70 or 80 seconds, and we would get the amount of charge. But the current is constantly changing. Okay? But what this equation suggests is that the product, if we multiply the current at any given time, multiplied by that, a small time interval, and we added all of that up, that would give us the total amount of charge which flowed through that sensor. So, well, we have a current versus time graph, right? Current on the y-axis, time on the x-axis. What is it about a graph that gives us the product of these two variables? Let's say the y variable and the x variable. We've done this before for other things like displacement on velocity versus time graphs. It turns out that the area of any graph tells you the product of the y variable and the x variable. So the area of a current versus time graph gives you the product of those two things, and we said that is the net charge which passed through the sensor. So the area gives us current times time, and we said that's charge. Now let's think about what are the units of this area. Well, you'd have the units of the current, kind of the height of this, that's amps or coulombs per second. And the width is, some amount of time in seconds. So coulombs per second multiplied by seconds. The second units cancel, and the units of the area just turn out to be coulombs, which is some amount of charge, and that's what we're actually after. So in order to do that, there's a button in Logger Pro that looks like this, and it's how you find the area under the data that's collected. And the fancy word for finding the area under some kind of graph is called an integral. So it's the integral button. So if you select the region where there is current. So select this, hit the integral button. It will shade all this stuff in, and it tells you the value of that integral, or which is again a fancy word for area. It's about 0.54, 0.5382, but about 0.54 amp seconds. And remember, an amp second is really a coulomb divided by seconds times seconds. That's essentially simplified. That's just a unit of charge. And so when we look at this, if the area is about 0.54, that means we can say that there's 0.54 coulombs of charge is stored in this specific capacitor when there was a 4.5 volt potential difference across the two conductive plates. So this would actually be one data point in our experiment. For a 4.5 volt potential difference, there's about a half of a coulomb of charge that's stored by that capacitor. One note about data collection, if you guys are going to be in the lab collecting data with this stuff, is that before you guys collect data, you want to make sure that the amp meter or the current meter is zeroed when there's no current flowing through it. So you just go up to the experiment tab and go down to press 0 when there's nothing connected to it. Then you also, under that same experiment tab, want to go to data collection, and you want to increase the duration that data is collected. The default might be like 10 seconds. So you want to make sure that it's collecting data long enough for that capacitor to become discharged. And you also want to change the sampling rate so that it's collecting 100 samples each and every second. You go ahead and click done, and then you can go ahead and collect data. So looking back at our purpose, remember our purpose is to determine the relationship between the amount of charge stored on the capacitor plates, the net charge on each, and the potential difference between those metal plates. And so you're going to be changing the potential difference that you're going to apply across the capacitor plates. And then for each situation, discharging it through our current meter, and then finding the area to figure out the amount of charge that was actually stored on those plates. And so, like we said, for 4.5 volts for that capacitor, maybe not yours, there's 0.54 coulombs stored on those plates. You'll do that for maybe 6 to 8 different data points, 6 to 8 different potential differences, and find out 6 to 8 different amounts of charge stored on those capacitor plates. When you go to graph this, we're going to graph our independent variable, the potential difference that we applied across the capacitor plates on the x-axis. That's what we deliberately changed by hooking different amounts of batteries up to the negative and positive plates. And then our charge, that's the dependent variable, we're going to graph that on the y-axis. And then you can go through and do the data analysis or the graphical analysis that we're used to doing. If this is linear, add a linear fit and find the equation for that line. If not, if this is non-linear, we're going to have to linearize that graph, make it appear linear so that we can add a linear fit, so we can come up with a mathematical expression or an equation to represent this relationship we're after, which is how the charge stored in a capacitor is affected by the potential difference. And one last reminder, this is how the setup looks. Use different amounts of batteries connected together in a row to force there to be a different potential difference across these two plates, right? You're charging the capacitor here, then you disconnect the batteries and basically make a conductive path from the negative side to the positive side with our current meter inside of there and our little device to kind of slow down the flow. This is where you're going to get your current versus time graph so we can figure out the amount of charge that was actually stored in that capacitor.